Hello, Royals. Lesson 6.2 on vector laws has a couple of problems where the solutions just didn't fit on the lesson. So let's run through it together. So follow along on the printed or digital lesson for 6.2. First thing I want to tackle is this idea from the end of the last lesson about the angle between two vectors. Question number 1 says two vectors measuring 3 centimeters and 5 centimeters are added. And if the angle between the vectors is 35 degrees, find the magnitude and relative direction of their sum. Okay, so the vectors are 35 degrees apart. That is the angle between them. That, by definition, is the tail-to-tail angle. There's an angle of 35 degrees. This vector right here has a magnitude of 3 centimeters. This vector right here has a magnitude of 5 centimeters. I like using the tip-to-tail approach or the parallelogram approach. And that right there is their resultant, which I think I'm going to label the vector r here. These diagrams can get a little bit messy pretty quick, so I think I'm going to split it up into a triangle here. Let's label that theta. I've got, this is a good time to switch to scalars, for example. I'm not super comfortable labeling this 3 centimeters because a vector needs a direction and a magnitude. But now this is just a scalar, and that's 3 centimeters, and that's 5 centimeters. And that right there, I will call the magnitude of r. I don't think it came up in the lesson. If you want to say mag r, you'll save a couple of seconds and you'll sound really cool too. We need to find theta. Theta is the supplement of 35 degrees. 180 degrees minus 35 degrees. If anyone asks why we're not using radian mode, just distract them for a second and hope they don't ask again. 145 degrees. And now I'm set to use some grade 10 trig, namely the cosine law to find the magnitude of the vector r. That's the resultant there. Mag r, see, is, let's say squared, is going to be 3 squared plus 5 squared minus 2 times 3 times 5 times the cosine of 145 degrees. It's calculator time. 3 squared plus 5 squared minus 2 times 3 times 5 times the cosine of 145 degrees. I'm in degree mode, of course. Square root of that, we'll say it's about 7.65 centimeters. Okay. Now, as far as the relative direction goes, I'll explain that in a second by sort of rotating things. I wasn't told that the vector of magnitude 3 centimeters is pointing north here. I didn't even know that the second vector was off to the right of this one. But I'm going to illustrate it doesn't matter how you orient these, you can still find a relative direction for this vector. This isn't something that happens a lot in physics. In physics, you usually have a fixed direction for forces. So I feel like to report the direction of this vector, I'd like to know that angle there. What angle haven't I used yet? I'll call it gamma. And I feel like I'm set up to use the sine law here. I'll say the sine of gamma divided by, I guess that would be 5, is going to be equal to, I'll use the sine of 145 degrees divided by mag r, 7.65. It's calculator time again. 5 times the sine of 145 divided by 7.65. And the inverse sine of that is about 22 degrees. So the way that I'll report this as a relative direction is I'll say that the resultant is 22 degrees off of the 3 centimeter vector towards or in the same direction. Notice in my parallelogram diagram, I think the word towards the 5 centimeter vector will make the most sense. Because here's the 3 centimeter vector, and I'm going to go towards the 5 centimeter vector. Let me write that down, and then I'll do some rotating and maybe some reflecting to try to convince you. So I'll say r is about 7.65 centimeters. And then for my direction, I'll say 35 degrees off I'm just going to be very wordy here. The 3 centimeter vector towards the 5 centimeter vector. What do they say, that brevity is the soul of wit? So be as detailed as you can. Okay, so what if my orientation was different? Am I going to rotate my page or rotate my camera? You'll never know. I did both. Actually, I did both at the same rate, so it didn't actually look like it was rotated. Here, let's just overdo it. All right, so what if this 3 centimeter vector was kind of going off to the left here a bit, and the 5 centimeter vector was going up? The resultant is still about 30. Oops, did I write down the wrong angle? Sure did. The resultant is still 22 degrees off of the 3 centimeter vector towards the 5 centimeter vector. Even if I had placed the 5 centimeter vector going in the opposite direction on the other side. Say this was the 3, and this was the 5, then there's the 3 plus 5, there's the resultant. The resultant would still be 22 degrees off of the 3 centimeter vector towards the 5 centimeter vector. Okay, that's relative directions. All right, next let's take a look at question number 3. In question number 3, we're given a cube. I'd like you to try question number 3 on your own, because I'm going to change this cube around. I'm going to show you the, again, idea of labeling in a cyclic order, that it doesn't really matter how I orient my cube. How is the cube done on the diagram? This was the cube for the diagram, with A, B, C, D being a base, I suppose. I'm going to make it a face, just to be different. So here's, I said I was going to make it a face. A, B. If I decide to put B there, C could be here or here. I'm going to put it over here, and then I'll put D down there. And now A, B, C, D, E has to be here, F has to be there, G has to be there, and H has to be there. And I was told that the vector AD was lowercase b, that AB was lowercase a. Not the greatest naming convention. Who came up with this? AE is lowercase c. Okay, and we are asked in question number 3 to write as an operation on A, B, and C. The first was the vector CF. So on my diagram, to find the vector CF, I'd like to name the vector CF with you. Notice it is the diagonal of one of the faces. For that reason, we call it a face diagonal. It is one of many face diagonals for this cube. Okay, CF is on my cube a vector that goes or comes forward and goes right. So to me, it looks like I need directions on these vectors. There we go. Looks like I need a vector that goes forward. Well, my vector B goes backwards or into the page. I want an opposite of B. So I'll do an opposite of B. That'll be that right there. And then I need a vector C. I can add that. So that would work just fine. Now that could be C minus B if you like. But notice the addition of the opposite works a little bit better than any sort of triangle methods of subtracting. You could try doing this with your relative vertices as well if you wanted to. You could say that CF is going to be CB, initial to terminal, plus initial to terminal, like that. Well, another vector equivalent to CB is DA. And another vector equivalent to BF is AE. And the vector dA, well, I define the vector B as the vector AD. That means if I'm looking for a definition for the vector dA, that's going to be the opposite of B. So I get the opposite of B plus C. And what you should notice is that even though I changed the orientation of the cube, that doesn't affect the answers at all. The answers from the printed lesson should be exactly the same. Let's try the second example. We were asked to find a vector equivalent to BH, or to write BH as operations on vectors lowercase a, b, and c. BH. BH, notice, goes all the way through the body of the cube. It is called a body diagonal. When we're working in 3 dimensions, we need to specify what type of diagonal we're talking about, whether it's a face diagonal or a body diagonal. Let's try this straightforward, or this approach first here. BH, to get BH, I could do BA plus AE plus EH. Notice, almost like a chain rule, how you go from B to A and from A to E and from E to H. That's equivalent to going from B to H. What's another name for BA? That looks like an opposite of A. What's another name for AE? That's a C. What's another name for an EH? That looks like a B. There you go. That operation should work just fine. Right. What was next on our list? Oh, yeah. Scalar multiplication. The reason why there is no scalar division. This is kind of a tricky conversation, because you've been used to working in the real number system, and in the real number system, there's all sorts of operations that have inverses, and now we're working with vectors, and vectors are not one-dimensional numbers. There was an awful lot of properties over the last couple of days about being vector addition or subtraction or multiplication being distributive and associative, and it's not really necessary that you memorize all of those. Some of them tend to be intuitive, but you want to be very careful, because not all properties that you know about numbers carry forward with vectors. So for the idea of no scalar division of vectors, let's just go back to scalar quantities, number quantities. We can say that if A times B is equal to C, then that means that B is going to be equal to C divided by A, and likewise A is equal to C divided by B. Okay, that's what we're comfortable with. So let's say I give you some vector u, which is a scalar multiple of the vector v. The question is, am I allowed to just divide both sides by a? Can I just perform division with vectors? Does the vector v equal the vector u divided by a? And the argument that I have, and I understand it's not the strongest one, is that if that were true, then you would kind of have to accept the fact that, what do I want to do here? Oh, let's divide both sides by v. The reason why you're not supposed to divide vectors by scalars is because you're not really supposed to divide vectors at all. This sentence should cause some discomfort for you. How could I divide two vector quantities and have the different distances like eliminate, or directions eliminate, directions eliminate and give me a scalar quantity? Since I would say that this doesn't make any sense to me at all, I don't see how the division of two vectors would give me a scalar, then I would have to say that no, I'm not allowed to do this. Okay. You will find people on websites doing that. You will also find people on websites saying that the fluorination of drinking water is the greatest communist conspiracy of the world. I don't know. Okay. Don't trust every mathematician, air quotes. Yeah. Mathematician that you find on the internet. If AV is equal to U, then what we can write in this course is that V is a scalar multiple of the reciprocal of A of the vector U. That's acceptable. we only have scalar multiplication of vectors, no scalar division. Okay. All right, last thing I want to do, even though I had like some of the numbers show up on the lesson, I just want to walk through question number 4 with you here, because it is it's a bit of a mess to follow, and there's no diagrams visible on the lesson. I might see if I can squeeze one in there, so you might find one by the time you watch this lesson. Okay, given u, mag u is 8 meters, mag v is 12 meters, and mag u plus v is 16 meters, determine the magnitude and relative direction of the vector 2u minus 3v. It seems a little bit overwhelming, but if you use a sketch, things can come into place. Your sketch does not need to be that accurate, though, so don't stress out over that. I want a vector of magnitude 8 units, a vector of magnitude 12 units, and the resultant to be a magnitude 16 units. I feel like that angle is going to be obtuse for that to happen, but again, don't worry too much about that. 8, 12, 16. There. Okay. Again, I'm labeling scalar quantities on a vector diagram. Not the greatest thing in the world. Here's the vector u. Here's the vector v. Here's their resultant u plus v. Okay. Now what I'm looking for is the magnitude and direction of the linear combination of vectors 2u minus 3v. And to do that, what I'm going to visualize is here is a v, here is an opposite v. Okay. So I'm just going to shift over here because the position of a vector doesn't affect its definition. And I'm going to sketch 2 u's and 3 opposite v's. There's a 1 opposite v, there's another opposite v, there's a third opposite v. Okay, so there's 2u. There's the opposite of 3 v's, or 3 opposite v's. And this right here is going to be the vector 2u plus 3 opposite v's, or minus 3v. Sorry. Okay. Now, I should be able to figure out if the magnitude of u is 8, the magnitude of 2u is going to be 16. Let's just always show where that number comes from. If the magnitude of v is 12, the magnitude of the opposite of 3v is going to be 3 times 12. It's a magnitude, so of course it's not negative 36. And then let's say the first thing that I'm looking for is the magnitude of this vector right here. It'd be nice to know at least one angle in this triangle to be able to figure that out. And what I notice is that I have a tip to tail angle right here between a u and an opposite of v. Or if you look at this diagram right here, let's call that, I don't know, I guess I'll call it theta. I think that's what I used in the lesson. There's theta right there. That is going to be, why am I confused right now? Oh, sorry, that's the angle between the vectors, isn't it? Opposite angle theorem. So here's my plan. I'm going to find, let's say, this angle right here. Using this triangle, I'll get its supplement, I'll find that angle, I'll find that magnitude. So over here, I'll say that the cosine of gamma is going to equal 8 squared plus 12 squared minus 16 squared, all over 2 times 8 times 12. What time is it? It's calculator time. 8 squared plus 12 squared minus 16 squared divided by 2 times 8 times 12. Inverse cosine of that. Gamma is about 104.5 degrees. Okay. That means that theta is going to be the supplement of that. Whoops. Watch how I save this. -1. Oops. It's about 75.5 degrees. And there. And now I use another cosine law to solve for this magnitude. Maybe we could just define this as the resultant so that I don't have to write that out again. Let's go over here and say the magnitude of this. It's not really the resultant, is it? I could label it some other symbol, but in the time I tried to save to avoid writing this out, I could have written that out 3 times. That magnitude squared is going to equal this magnitude squared plus this magnitude squared minus 2 times the product of those magnitudes multiplied by the cosine of the angle in between them, 75.5 degrees, which gets me calculator time, 16 squared plus 36 squared minus 2 times 16 times 36 times the cosine of 75.5. And I'll take the square root of that. I get about 35.5 meters, depending on when I round it off. A couple more triangles would have helped here, maybe like a scalar triangle instead. I've got a magnitude of 36, 16, 35.5-ish. And for the relative direction, like on our first example, I'm going to find, what angle haven't I used? I don't know, I'll call it beta, I guess. And I'm set up to use the sine law to solve for beta. I'll say the sine of beta divided by 36 is going to equal the sine of 75.5 degrees divided by 35.5. And get that beta is going to be about 36 times sine 75.5 divided by 35.5. Inverse sine of that, about 79 degrees. And here comes our conclusion with this relative direction here. Okay, let's go back right here. There's u, here's v, going off in that direction. And this is the vector that we're trying to report. So I will say that 2u minus 3v is, I guess, a vector roughly equivalent to a vector with a magnitude of 35.5 meters going in a direction of 79 degrees. I'm going off of u and then not towards v, but away from v. Okay. Some physics students in the past that ended up in my vectors class have tried to start a question like this and say, assume that u is going east. Well, yeah, that's going to make things a little bit easier, but there's your first mistake. You shouldn't have to assume that u is pointing east. It would make your direction a little bit easier to report, and we're not looking for the easiest way to get one specific answer. We want an answer that is going to be true no matter how you arrange these vectors. Okay.